Question number 10, derived from current, electricity, and more specifically, the experimental part. The question is related to meter bridge. Let's see what the question has to say. A meter bridge, the wire of length 1 meter, quite obvious, has a non-uniform cross-section such that the variation dr by dl of its resistance R with length is this. So dr by dl is inversely proportional to root of L. And let me just try to show you the figure that would make the matter more easier. So there is the situation. Here you see this is the meter bridge and the wire is non-uniform, which is very clear. And this length is L, this is 1 minus L, of course, for the sake of reference that has been drawn. And it says two equal resistances are connected as shown. So this is R dash and this is also R dash, two equal resistance. The galvanometer has zero deflection when the jockey is at point P. What is the length AP? Quite obviously it can't be mid because the meter bridge's wire is non-uniform. So essentially what am I supposed to do is that let me calculate this resistance and let me calculate this resistance. So let's try to see. In order to calculate the resistance, what I'll do is that dr by dl has been given as this much. So I can write K by root L dl will be the small resistance, K being the constant which occurs for this given expression. And this is the small resistance. And if I put the limit of 0 to L, let me call it as R1, where R1 would be the resistance of this portion. So let's try to calculate the resistance. To integrate is not a problem at all. So that's going to be 2K root L and the limit will go from 0 to L. So the resistance is 2K root L, the resistance of this portion. That we have named it as R1. And now I would like to calculate the resistance of this portion. Instead of putting the limit from L to under root 1 minus L, what we can easily do is that let's find the resistance of the entire part and let's just subtract it. So in order to calculate the resistance of the entire part, what I can do is that, say, I can put the limit from 0 to 1. That can be done. So if I put the limit from 0 to 1, that's going to give me 2K. So 2K would be the resistance of the entire part. So of this part, if I call it as R2, that is going to be 2K minus 2K root L. That's the resistance of this. And for the given condition, it has been said that the galvanometer is showing zero deflection. That means it has to be a balanced whetstone. Since these two resistances are equal, so this and this also need to be equal. So the condition is R1 equals to R2. Go for a little bit of solving. You would get option number 3 as the correct option for question number 10. So for question number 10, the correct option stands out to be option number 3. That's fine. Now let's go to the 11th question. Question number 11 is a beautiful combination with so many different forms of gate. And even in my previous segment of discussions, I had said, particularly from those topics which are excluded in JEE advanced list, they form an integral part of question for JEE main. Therefore, topics like magnetism and matter, semiconductor, principle of communications, these which are not included in JEE advanced syllabus has to be taken with extra care. So here it's a combination of NAND and OR gates. Let's try to see. We need to find the ultimate output Y. Okay, to do that, what we'll do is that let me call this output as P and this output as Q for the sake of simplicity. Fine then, now let's see what can P be written as. You could see that P is the NAND of this and this. So that's going to be A into AB bar. That's an output of this. So this is AB bar, this is A, and that has been NANDed here. Now we can use the De Morgan's expression. You break the bar and change the sign. So that's going to be break the bar and change the sign. So that will be AB. Now see, double bar, that's going to be AB simple. So that's P. Fine. Now let's talk about Q. What is Q? If you see Q, Q has the OR output of this and this. So to see what is Q, the expression of Q comes something like this. One input is AB bar and the other input is B, and that has been ORed, so that's plus here. In fact, it's not plus, that's an OR gate, but the symbol is of plus. Now let's further manipulate it. This is A bar plus B bar plus of B. Fine. Again using De Morgan's here. Now this thing is going to be 1, and 1 plus A bar again is going to be 1. So the output at Q, that's going to be 1. So there is P, there is Q, and P and Q are NANDed. So ultimately the output Y would be PQ NAND, and a simple of the calculation, eventually this thing will be AB bar, so leading to this as the correct option. So question number 11 has second option as the correct option. Let's move to question number 12. Question number 12, a very straightforward question related to computation of magnetic field. And here's the question. The question has two infinitely long wires bent at 90 degrees in this given format. And the question also says that this distance equals to this distance, which is 4 centimeter, call it as R, and the net magnetic field at O that has been given, which is 10 raised to the power minus 4 Tesla. Assuming current in both the wires to be same, we are supposed to calculate the direction of magnetic field at O and the magnitude of the current carried by each wire under the assumption that the current is same. Well, if you see, the magnitude of the magnetic field by this is going to be 0, by this is going to be 0. So this will produce mu naught I by 4 pi r. The next one is also going to produce the same. So you multiply it by 2, and that is going to be the net magnetic field. Why did I multiply by 2? Because a simple right-hand curl rule would say the direction of field due to this and due to this at this point would be same. And the value of semi-infinite wire creating magnetic field is this much. Now B is given, R is given, you can easily calculate current, and the value of current would be 20 ampere. As far as the direction of magnetic field is concerned, it's so clear the magnetic field would be into the phase. So option number 2 is the correct option for question number 12. Time to move to question number 13.